exponential families. There is a class of distribution which has the complete and sufficient statistic is called the exponential family or exponential class. Consider a family that is f of x theta, theta belong to its parametric space, or the probability of the probability density function or the probability mass function, where the parameter space, that is theta, from alpha to beta, where alpha and beta are the constant, or it may be from minus infinity to plus infinity. That is actually the general terms alpha and beta. It could be anything. It could be minus infinity. It could be up to a positive infinity. And the form of this family is, that is f of x theta, that is exponential p theta, k of x, h of x plus q of theta, and x belong to S and 0 elsewhere. So where S is actually the support of X, the one has the following characteristics. So the form of the exponential has the following characteristic. Number one, S does not depend on theta. The support, which means that कि जो आपके range होगी उसमें आपका parameter theta involved नहीं होना चाहिए. The second thing is that P of theta is non-trivial, continuous function of theta that belongs to the parameter space. And if x is a continuous, then k dash x is not equal to 0, and h of x is a continuous function of x belong to S. And if x is a discrete, the k of x is a non-trivial function of x belong to S. In this course, we just focus on the specifically exponential class of family that is called the regular exponential class of families. So it means that if we are able to present our probability density function in the form of 1 as given in equation 1, and it has the following characteristic which just I specified now, then we say that it has a complete and sufficient statistic. So we just only need to show our probability density function in the form of that which is given in equation 1, and if it also possesses the following three characteristics, when we say that yes, it has a sufficient and complete statistic. So just for example, we just show that how we can show that a probability density function is a sufficient and complete statistic by writing in that equation number in the form of equation number 1. So let's take an example of the normal distribution. First of all, we have the probability density function of the normal distribution, that is f of x theta, that is 1 over 2 pi theta e raised to power minus x square over 2 theta. So we can easily write this equation in terms of exponential form. So we just take the exponential and taking the log of the other terms which is not involved in the exponential. So this term e raised to power minus x square over 2 theta can be written as in terms of exponential, that is minus 1 over 2 theta x square, minus the rest of the term can be incorporated in the exponential function by taking the log of these terms. So that is actually written as minus log under root 2 pi theta, and that x has the range from minus infinity to plus infinity. So you can see that we can write the normal distribution in terms of equation 1, which represent the exponential family. Similarly, if we take the example of the uniform distribution, that is actually 1 over theta and it ranges from 0 to theta. So we can write this function in terms of equation 1, that is, you can see that that is exponential minus log theta, because that is 1 over theta, and when we take the log, that is actually minus log theta. But the problem is that the support of x, that involves actually theta. So here you can see that x belongs to 0 to theta. So it means that theta involves its support. So it does not fulfill all the characteristics which is given for the exponential family. So we can see that although we can write the uniform distribution in terms of exponential form, but one condition that the parameter does not involve in the support, which is not fulfilled in this case. So we can say that this is not follow the form of 1, and because it involves the theta in the support, so it means that it depends upon the theta. So hence it is not a regular class of exponential family of distribution.